Hi friends, welcome to our YouTube channel Naraj Academy. The main aim of this lecture is to discuss about the AP-SPDCL 2019 question paper of the AE of EE in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button so whenever we upload a new video, the direct notification comes from a while. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. So now we are going to solve the 11th question. See the question here. An EMF of 1.5 kilovolt is induced in the coil when a current of 4 ampere collapses uniformly to 0 in 8 milliseconds. The inductance of the coil is. So basically they are given an inductor coil. So in this inductor coil, an EMF of 1.5 kilovolt is going to induced when a current is going to uniformly collapse from 4 ampere to 0 ampere in a time period of 8 milliseconds. So based on this data, we need to find what is the inductance of the coil we need to figure out. So what are the four options? Option A, 3 Henry is the correct solution of this question. So let's solve this numerical. So basically this is the inductor. The voltage across the inductor is V and the current through the inductor is I. In the question they are given that the current is going to uniformly decay from 4 ampere to 0 ampere in a time period of 8 milliseconds. So during this period, what is the EMF which is induced in the inductor? They have given, which is 1.5 kilovolt is the EMF which is going to induced in the inductor. So based on this, we have to find what is the value of the inductor we need to figure out. So basically the expression of the voltage and current in the inductor is V is equal to L into di by dt. So we need to know what is the magnitude of the current only we need to find, which is rate of change of the magnitude of the current we need to figure out. So basically here the initial current is 4 ampere and the final current is 0 ampere. So therefore the rate of change of current, which is final value of current minus initial value of current, which is 0 minus 4, it is nothing but minus 4 ampere. And what is the time period? So what is the time period for this decay? So dt is equal to final time period minus initial time period, which is time period difference is 8 milliseconds. So blindly substitute those values here. So 1.5, the voltage is 1.5 into 10 to the power of 3 is equal to L into, see, all we need to know is only the magnitude of the rate of change of current, which is 4 by 8 into 10 to the power of minus 3. So if you solve this one, now L is equal to, so do the into and divide here. Finally we are going to get this expression, and if you solve this expression, we are going to get finally L is equal to 3 Henry. So therefore the inductance of this coil, which is 3 Henry, is the correct solution of this question. So now we are going to solve the 12th question. See the question here. The graph shown in the figure represent RLC has constant values. So basically they are given as some graph. So we have to find what is this graph it is going to represent for a series RLC circuit. So based on these options, option B, mod of XC versus frequency. This is a graph which is going to relate the magnitude of the capacitor reactance versus the frequency diagram. So say something more about this one. So basically this is a series RLC circuit. Resistor, inductor and capacitor, and the voltage across this is V of t, which is the source voltage, and the current is I of t. So now basically see here what is the net impedance of this circuit. So the net impedance of the circuit is R plus J of XL minus XC. But I want to know what is the magnitude of the impedance, which is mod of Z is equal to under root or R square plus XL minus XC whole square. So now what I am going to do is I am going to find what is the nature of this impedance magnitude with respect to the frequency. So if you see carefully, for a series RLC circuit, this is a diagram we are going to get like a tub shape. So here at this frequency the value of the impedance is very low. So it is equal to resistive part. So therefore this frequency is called as a resonance frequency. So at this frequency the circuit will be purely resistive. So therefore the supply voltage and the supply current will be both in phase. And this is FL and FH is called as the FL is called as a low power half power frequency, and this is a high half power frequency. So therefore here this is root 2 R. At these frequencies we are going to get the net impedance of the circuit, which is root 2 into R. So for a frequency less than resonant frequency, the capacitive reactance will be very high when compared to the inductive reactance. So therefore the circuit will act like a capacitive circuit. And similarly at resonant frequency the inductive reactance is equal to capacitive reactance. So therefore net we are going to get only the resistive. So therefore the circuit will be purely resistive part. And similarly for a frequency which is greater than the resonant frequency, the inductive reactance will be very high when compared to the capacitive reactance. So therefore we we are going to get a inductive circuit. But this will be opposite for a parallel RLC circuit. For a parallel RLC circuit, for a frequency less than f0, it will be inductive nature, and for a frequency is equal to f0, we are going to get a resistive nature, and for frequency greater than f0, the circuit will be capacitive nature for the parallel RLC circuit. So now I want to know what is the diagrams of the reactance and inductance, reactance of the capacitance and the reactance of the inductor with respect to frequency. So basically x is equal to 1 by omega c. So omega is called as a 2 pi f c. So 2 pi f. So in place of omega I am going to substitute 2 pi f. So therefore 1 by 2 pi f c. So I want to know what is the relation with respect to the reactance of the capacitor and the frequency. So these both are inversely proportional. So therefore x is inversely proportional to frequency. So therefore this is the diagram we are going to get. At lower frequencies we are going to get the high value of the reactance. As the frequencies goes on increases, this reactance goes on decreases. So like a hyperbola shape we are going to get this one. So this is the diagram between the capacitor reactance versus the frequency. In the question they are given this diagram and they are asking this diagram is going to represent between what parameters. So therefore it is a diagram between the XC and the frequency. And similarly now I want to draw the diagram for the inductance reactance versus frequency. So inductor reactance is equal to omega L. So I am going to replace omega by 2 pi f. So therefore 2 pi f L. So if you see the relation between the inductor reactance and the frequency, these both are directly proportional. So therefore XL is directly proportional to frequency. So this is the diagram we are going to get. See, at lower frequencies the inductance reactance is very low. As the frequency increases, the reactance also goes on increases. So because of this nature only, see, at lower frequencies, if you compare these two diagrams, at lower frequencies inductive has a high value of reactance when compared to inductance of the, at lower value of the frequencies the capacitance has high reactance when compared to inductor. So therefore it is act like a capacitor circuit. At higher frequencies capacitance nature is very low, but the inductance is very high. So because of this it is going to act like an inductive circuit. And if you want to know what is a current diagram in the RLC circuit, which is the current is going to follow like this shape. So at resonant frequency the current will be very high because the impedance is very low, and here at lower half power frequency and higher half power frequencies the current magnitude will be I max by root 2, because at this current, at this value of current we are going to get the half of the power of the maximum power. So half the maximum power we are going to get at these two conditions. So also if you want to know what these are the important formulas which are going to ask in any AE examinations, which is the bandwidth is equal to highest frequency means high half power frequency minus low half power frequency. So therefore, and the tau, what is the zeta? So we can say zeta, what is the damping ratio. So what is the damping ratio of this series RLC circuit, which is zeta is equal to R by 2 under root over C by L. So the zeta, the damping ratio of the series RLC circuit, which is R by 2 under root over C by L. But if you want to know what is the quality factor, which is Q is equal to 1 by R under root over L by C. So if you want to find what is the relation between the zeta and Q, we are going to get zeta is equal to 1 by 2 into Q. This is a very important formula. Based on these formulas, lot of questions are being asked in any AE exam. So finally here in this question they are given this graph and they are asking this graph is going to represent between what two parameters, which is reactance and the frequency. So now we are going to solve 13th question. See the question here. The magnetic field due to a current carrying conductor takes the form of. So basically here in this question they are asking what is the nature of the magnetic field whenever any current is going to pass through a wire. So what is the nature or the shape of this magnetic field? So what are the four options? Option A, concentric circles. So the wire is going to carry the current, so therefore it is going to produce the magnetic field in concentric circles. So now we'll discuss something more about this one. So basically here, now suppose this cross indicates the current is going into the board, and here the dot indicates the current is going outside the board. Suppose there is a wire, so there's a wire like this. Suppose that there is a wire like this and the current is going inside the wire. So therefore now what is going to happen here, by using the right hand thumb rule, so we have to keep the thumb in the direction of the current and then we have to curl the remaining fingers. The curl of the fingers is going to represent the direction of the magnetic field. So therefore here if you do like that, the thumb indicates the current. If you face the thumb in the direction of the current and if you curl the fingers, the curl is going to indicate the direction of the magnetic field. So therefore the magnetic field direction will be like this one, clockwise direction. So this is the nature of the magnetic field, which are the concentric circles. But if here the current is coming outside the board, the dot indicates the current is coming outside the board, and if you keep the thumb in the direction of the current and if you curl the fingers, the curling of the fingers is going to represent the direction of the magnetic field. So now these are in the anti-clockwise direction. So therefore this is the anti-clockwise direction. So this is the direction of the magnetic field in a current in a wire. So basically, so therefore we can conclude that due to wires, due to any current in a wire, they are going to produce a magnetic field in concentric circles. Suppose this question is also very famous in the A examination. Suppose the two wires are going to carry the current in the same direction, then what is the nature of the force between them, whether it is attractive or whether it is repelling, that we want to figure out. So basically, in order to solve this one, we have to know the basic formula, which is the force direction is equal to the F cap is equal to I cap cross B cap. So always, because of current in a wire and due to the presence of magnetic field, the force direction will be F cap is equal to I cap cross B cap. So if you see carefully here, this is a current carrying conductor. So this current carrying conductor is going to produce a magnetic field. If you place the thumb in the direction of the current, then this is going to produce the curl fingers like this one it is going to produce. So therefore the nature of this will be like this one. So here it will be inside there, it will be inside. So for this connector, because of this connector wire, this is going to produce a curl, a magnetic field inside this wire. So therefore here, if you see carefully here, this is a wire, right? So for this wire the current is upward and here the magnetic field is like this one. So you have to take the cross product, I cross B. This is a current and this is a magnetic field. So I cross B, if you do this one, the thumb is going to represent the direction of the force. So therefore the force will be in this nature. So because of this wire, there is a force on this wire in the direction of this one. And similarly, now find what is the direction of the force for this wire based on this wire. So if you take the thumb in the direction of the current, it is going to produce the magnetic field in this direction. So therefore for here it will be outside the wire, it will be coming outside, and here the current is upward. So current is upward and the magnetic field is like this one. So if you take the cross product, I cross B, the force is like in this direction. So therefore the force is in this direction. So if you see carefully, these both are attractive force. So therefore whenever any two conductors are carrying current in the same direction, there will be an attractive force. This is a very much important question. And similarly, suppose if they are going to carry current in the opposite direction, it will be a repelling force. So you can check even this also, which is a repelling force. This is a repelling force. So you can check by using this same formula, which is F cap is equal to I cap cross B cap. So I will check for you. See, the current is going to carry the current in this direction. So take the thumb and take the curl. So therefore on this wire, the magnetic field will be inside. So therefore let me assume the magnetic field is inside and the current is downward. So I cross B. So this is I and this is B. So I cross B, which is outside, the force is outside. So on this wire the force is outside. And similarly for this wire, the current is downward. So take the curl. So here the magnetic field on this wire will be inside. So therefore it will be inside and the current is upward. So therefore now take the cross product, I cross B. Again the force is outward. So therefore here there is a repelling force. So whenever any two wires connected in the same direction, there will be attractive force, and whenever the two current carrying connected in the opposite direction, then there will be a repelling force. So therefore these wires is going to repel of each other. So now we are going to solve the 14th question. See the question here. The average power in a 25 ohm resistor when it passes a current of I of t is equal to 2 plus 3 sin omega t plus 2 sin 2 omega t plus sin 3 omega t amperes. So basically here there is a resistor 25 ohms and the current which is going to pass through this resistor is, they are given some expression. So now we have to find what is the average power we need to figure out. So what are the four options? Option B, which is 275 watt, is the correct solution of this question. So let's solve this numerical. So basically there is a resistor of 25 ohm and the current which is going to pass through this resistor, which is I of t, and they also given the expression of the current I of t. This is a big expression they have given, and the resistor is 25 ohm. So based on this we have to find what is the average power consumed by this resistor we need to figure out. So which is P average we need to figure figure out. Basically, the power, the instantaneous power is equal to I square R. So therefore, I of t whole square R. So I want to find what is the average power, which is 1 by t integration of 0 to t I of t whole square into R dt, which is integration of the power by time period. We are going to get the average power. So the resistor is a common, it's a constant one. So I am going to take outside the integration. So therefore, R into 1 by t integration of 0 of t I of t whole square dt. This is nothing but IRMS. This expression is going to indicate square of the IRMS. So therefore, I am going to replace this integration of this whole data with a IRMS square into R. So basically, so therefore, PRH is equal to IRMS square R. So if you know what is the value of the IRMS, then we can substitute them and we can solve them. So now we need to find what is the IRMS values of this current I of t. We need to figure out. So basically, let me tell a small formula here. Suppose f of t is equal to summation of like this, f1 of omega 1t plus f2 of omega 2t plus f3 of omega 3t, like this up to fn of omega nt. Suppose f of t is a summation of all these things, then what is going to happen? Whether it is plus or minus also you can include there. It is plus or minus, plus or minus, plus or minus. So here, suppose this omega 1 and omega 2 and omega 3 up to omega n should not be equal. This is a condition you have to remember. All this omega 1, omega 2 and omega 3 and up to omega n, they should not be equal. They all have to be different. At that condition here, the net RMS of this f of t is equal to under root over square of each of the RMS of each and every signal. So you have to take the square of the RMS of each and every signal and you have to add here. No matter whether it is a positive or negative, always you have to add here. So this is a formula here. So if you see carefully here, I of t, see here omega is equal to 0, here omega is omega, and here omega is 2 omega, and here omega is 3 omega. So all these are different omega. So therefore we can conclude that here each and every signal has different omega. So we can blindly figure out the RMS of this current I of t, which is we have to find what is the RMS of each and every value and then you have to square that one. So the RMS of this DC is same. The RMS of this DC will be always same as the DC. But the RMS of this signal is 3 by root 2, which is peak by root 2, Vm by root 2. And here also the RMS of this sinusoidal is Vm by root 2, which is 2 by root 2. This is RMS value. And for the sin 3 omega t, the peak value is 1. So therefore the RMS value will be 1 by root 2. So now we have to do square and we have to add and then we have to take the whole square root. So therefore IRMS is equal to square root of RMS of DC, which is 2 whole square. This is 3 by root 2 whole square plus 2 by root 2 whole square plus 1 by root 2 whole square. So RMS of each and every term we have to take and then we have to square therefore. So then we are going to integrate finally under root over 11. So here the net formula is PRG is equal to IRMS square R. So we know the value of IRMS, which is root over 11. So you have to do the square into 25, which is 11 into 25 is nothing but 275 watt. 275 watt is the correct solution of this question. So blindly you have to remember the average power is equal to IRMS square R. So if you calculate the value of the IRMS, then it is very easy to solve. So this is a very, very important formula. Whenever all these omegas are different, no matter whether you add the signals or whether you subtract the signals, the net RMS value be square root of the RMS of each and every signal. You have to square and then you have to add. So for DC, the peak value for DC, the constant itself is average and also itself is indicates the RMS value. But for sinusoidal, the RMS value is Vm by root 2. So based on this, we have figured this question. So the correct solution of this question is average power is equal to 275 watt. Now we are going to solve the 15th question. See the question here. Ampere second is same as. So basically here in this question they are asking what is the ampere second. So what are the four options? Option A, Coulomb is the correct solution of this question. So let's solve this numerical. So basically current is equal to rate of change of charge with respect to time. So in this much time, how much amount of charge which is flowed. So if you take the ratio, that is called as the current. So therefore Q is equal to I into T. So the SI unit of the current is ampere and the SI unit of time is second. So therefore ampere into second is the unit of the charge, or we can say the SI unit of the charge is Coulomb. So therefore the SI unit of charge is Coulomb, or we can also say which is ampere into second. So therefore these are the two units for the charge, which is Coulomb or ampere second. So therefore we can conclude that ampere second is also called as the Coulomb. So this is the correct solution of this question. So now we are going to solve the 16th question. See the question here. The SI unit of magnetic flux density is. So in this question they are asking what is the SI unit of the magnetic flux density. So what are the four options? Option B, Tesla is the correct solution of this question. So let's discuss something more about this one. So basically the magnetic flux density, which is the ratio of the flux per unit area. So in a given small amount of area, how much amount of flux which is passed, it is called as the magnetic flux density. So where B is called as the magnetic flux density and phi is called as the flux, the SI unit is Weber and A is called as the area, which unit is meter square. So therefore, if you want to know what is the dimension of the magnetic flux density, then the ratio of the dimension of the flux per dimension of the area. So the dimension of the flux is Weber, the dimension of the area is meter square. So Weber per meter square is also called as the Tesla. So Tesla is another unit or SI unit of the magnetic flux density. So basically this Tesla is the unit for the magnetic flux density. Tesla was given based on the scientist name, which is Nikola Tesla. So basically Nikola Tesla is a very great scientist. He had spent a lot of his time for the inventions of the AC motors and the AC currents. So you can see there is a AC war between Thomas Alva Edison and the Nikola Tesla. So it's a very great thing, and also here because of his contribution there are so many things which has happened. So based on his remembrance, the magnetic flux density unit is also given on the scientist name, the Nikola Tesla, which is Tesla. So basically all the scientists call Nikola Tesla as a man who is very ahead of his time. So on the time, because of his ideas we can't implement, but now as the time goes on, all these ideas and all his inventions can be practically implemented. So basically all scientists call him a man who is ahead of his time. So this is that Tesla is the correct solution of this question. So now we are going to solve the 17th question. See the question here. Siemens is the SI unit of. So basically in the question they are asking, so Siemens is the SI unit of which of the quantity? So what are the four options? Option B, reluctance, is the correct solution of this question. So let's solve this numerical. So basically the relation between the conductance and reluctance is conductance is equal to 1 by reluctance. It is the inverse of the reluctance, is called as a conductance. So therefore the unit of the reluctance, the SI unit of the reluctance is ohm. So therefore the unit of the conductance will be 1 by ohm, or we can also say, which is 1 by ohm is also called as a mho, or we can also call it as a Siemens. So therefore the SI unit of the conductance is either mho or Siemens is the correct solution of this question. And let us also know some of the basic units for the light one. Now let us know some of the important units, which are the illumination. For illumination the unit is lux, and for the luminous flux the SI unit is lumens, and for the luminous intensity, which is the ratio of the lumens per steradian. So candle is also called as the lumen per steradian. And the lamp efficiency or the luminous efficiency, the SI unit is lumen per watt. So therefore these are the some of the basic units which are asked in every AE examinations, especially TS Genco like that examinations. These units are of very high priority. So therefore illumination the unit is lux, and for luminous flux the SI unit is lumens, and for the luminous intensity the unit is candela, or you can also say which is lumen per steradian, and for lamp efficiency or the luminous efficiency the unit is lumen per watt is the correct solution of this question. So these are the some of the basic units which are always asked in TS Genco like AE examinations. So basically the unit of the conductance is mho, or we can also say it as a Siemens. So now we are going to solve the 18th question. See the question here. If a function f of t is odd, then its Fourier coefficient satisfy. So if a function is odd, then what is the nature of the Fourier coefficients? So out of the four options, option D is the correct solution of this question, where a0 is equal to 0 and an is equal to 0, but bn is not equal to 0. So let us solve this one. Basically, as per the Fourier series, any periodic signal we can represent in summation of the sine and cosine waveform, which is f of t is equal to a0 plus sigma n is equal to 1 to infinity an cos nt plus bn sin nt. This is a standard representation for any periodic signal we can write in terms of the cos and sine series. So this is called as the Fourier series coefficients, which are the a0, an and bn. So we need to find the Fourier series coefficients a0, an and bn. So these are the three simple formulas, which is a0 is equal to 1 by t integration of 0 to t f of t dt, and an is equal to 2 by t integration of 0 to t f of t cos nt dt, and similarly bn is equal to 2 by t integration of 0 to t f of t sin nt dt. So these are the very standard equations. Suppose if f of t is even function, f of t even function is f of t is equal to f of minus t, then we can say it is a even function. Then what is going to happen? Suppose if it's a even function, integration of any even function, it is going to lead not equal to 0. And similarly, if f of t is even and cos is also even function, so therefore if you take the product of the two even functions, the resultant will be always even function. So if you take an integration of even function, again it is not equal to 0. But if you take a even function and sine is a odd function, so even into odd is again odd function. So if you take odd function, the total area, so positive and negative will be like this one. So is the positive area and is the negative area. So overall area will be 0. So therefore it will be equal to 0. This is for the even function. So whenever the f of t is a even function, a0 is not equal to 0, an is not equal to 0, but bn is equal to 0. Same thing I have written. So whenever the f of t is an even function, a0 is not equal to 0, an is not equal to 0, but bn is equal to 0. Then if f of t is odd functions, means here f of t is equal to minus of f of minus t. This is called as an odd function. So if f of t is odd functions, then what is the nature of the Fourier series coefficients, which are the a0, an and bn. Suppose if f of t is odd function, then integration of odd function, it is going to lead you total 0 value. And similarly here f of t is odd and cos is even. So odd into even is again it is going to give you odd function. So integration of odd function is again 0. So therefore this is a 0. And similarly here, if f of t is odd and sine is also odd, so odd into odd we are going to get even nature. So integration of even function, it is not going to equal to 0. It is not equal to 0. So we can conclude that for an odd function, a0 is equal to 0, an is equal to 0, and bn is not equal to 0. So therefore a0 is equal to 0, an is equal to 0, and bn not equal to 0. So these are the relations of the Fourier series coefficients for the even function and the odd function. In the question they have asked only what are the Fourier series coefficients nature when f of t is odd function. So therefore a0 is equal to 0, an is equal to 0, and bn is not equal to 0. This is the correct solution of this question. Now we are going to solve the 19th question. See the question here. The unit impulse response of the system whose transfer function is. So basically they are given transfer function which is 3s by s plus 2. So based on this we have to find what is the unit impulse response we need to figure out. Means when we are going to give input as delta of t, then what is the response h of t we need to figure out. Here out of the 4 options, no option is correct. Means there is no solution for this question. Means all the options which are given in this question are incorrect. So let us solve this numerical. So basically this is a system. The transfer function of the system is h of s is equal to 3s by s plus 2. See here the input is r of t and the output is c of t. Suppose input is equal to impulse unit which is delta of t. If the input is delta of t, which is delta of t is the input, then what is the nature of the output? See here, for input delta of t, the output will be h of t. So therefore we can assume c of t is equal to h of t. So if the input is r of t, the output we are going to get c of t. This is the general inputs. But if r of t is equal to delta of t, the output we are going to get is h of t. H of t is called as a unit impulse response, which is c of t. So I want to find what is this response h of t, we need to figure out. So here the Laplace transform of output by the Laplace transform of input is equal to transfer function. So therefore the Laplace transform of output is c of s by r of s is equal to h of s. In the question they are given h of s is equal to 3s by s plus 2. So here c of s is equal to, I am going to take r of s to the right side. So therefore 3s by s plus 2 into r of s. So for r of t, the Laplace transform of r of t will be equal to 1. So therefore 1 is the Laplace transform of the delta of t. So therefore in place of r of s I am going to substitute 1. So therefore 3s by s plus 2. So now I am going to do the simple like this. So 3 common here. I am going to replace s by s plus 2 minus 2. Same thing I am going to get here. So now I am going to do the division of this one, which is 3 into s plus 2, which is s plus 2 by s plus 2 minus 2 by s plus 2. So s plus 2 by s plus 2 we are going to get here. This is the 1. So therefore 1 minus 2 by s plus 2 is the simple one. So now I want to do the Laplace inverse. So therefore c of t is equal to h of t is equal to the Laplace inverse of 1 is delta of t, and the Laplace inverse of 2 into 2 by s plus 2 is equal to 2 into e to the power of minus 2t, because the Laplace inverse of e to the power of minus 80 we are going to get 1 by s plus a. So based on this formula we have done the conversion. So therefore here, so I am going to take 3 inside. So therefore 3 into delta of t minus 3 to the 6 into e to the power of minus 2t. So therefore this is the correct solution of this question. So whenever you are going to give the impulse unit impulse for the system, for this transfer function, the output we are going to get, which is 3 into delta of t minus 6 into e to the power of minus 2t. This is the response we are going to get. But this option, this answer is not present in any of the options. So therefore, this is the correct solution of this question. So this is the last question of this lecture. So the question here, the transfer function of the DC servo motor EB of s by omega of s can be expressed as, where kb is a constant. So basically in this question they are asking what is the transfer function of the output by input, where output is a back EMF and input is a speed in the terms of radians per second. second. So RPM, so omega is the RPM. So based on this here, sir, omega is the radians per second. So based on this we have to find what is the ratio. So here, what are the four options? Option C, KB. KB is the correct solution of this question. So let's solve this numerical. So basically this is a DC servo motor. For this DC servo motor here, the output is AB of S and the input is omega of S. So now you have to find what is this transfer function we need to figure out. So transfer function is the Laplace transform of the output by Laplace transform of the input, which is EB of S by omega of S. We need to find the relation between them. So basically for a DC motor, the back EMF relation is EB is equal to P phi into N by 60 into Z by A, where P is called as the number of poles and phi is called as the flux per pole and N is the speed in RPM and Z is number of armature connectors and A is called as the number of parallel paths. So based on this here, what I am going to do is, now I am going to divide 2 pi and multiply 2 pi. So therefore same thing we are going to get here. So I divided by 2 pi and I multiplied by 2 pi. So if you see carefully, this 2 pi N by 60 is called as the omega in radians per second. So I have replaced this 1 by omega and remaining everything I have written same. So if you see carefully here, except omega, see I am going to replace omega outside. So therefore Z by A into omega. So here this term, this is a constant term, because whenever you fix the motor, the number of poles are fixed and the flux per pole is also fixed and the number of armature connectors are fixed and the number of parallel paths are also fixed, because you fix the motor windings. So therefore all these things are the constant for a motor. So therefore this is called as a KB. So therefore this is called as a, all the coefficients, these constants I am going to replace by a constant which is a KB, and this is the omega. So therefore whenever, so EB is equal to KB into omega. So in the term of time domain, EB of t is equal to KB into omega of t. See, as the omega is changing, the back EMF is also going to change, but KB is a constant for a particular fixed motor. So therefore now I am going to take the Laplace transform. So therefore EB of S is equal to KB into omega of S. So I want the ratio of EB of S by omega of S, which is equal to KB. This is what we need. So therefore AB of S by omega of S is equal to KB. So therefore this is the transfer function of this DC motor if the output is back EMF and the input is a speed in terms of the radians per second. So therefore KB is the correct solution of this question. So by this lecture we have successfully completed the 20 questions which are the previous year questions of the AP-SPDCL 2019 question paper of AA of AE in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button, so whenever you upload a new video, the direct notification comes to mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling, take care and bye bye.